This module is all about different ways to describe and compare pros and cons of the different conservation drainage practices we've been discussing. If you're completing some of the other modules in this course, you'll have learned about some of the conservation drainage practices by now. When you step back and look at all of the options together, it's useful to compare the practices in context of each other, and there are lots of ways the practices can be compared. We'll start with one of the most obvious from a water quality perspective. How well do these practices work for reducing nitrate loss in tile drainage? Curiously, until around the time that the nutrient strategy started to be developed in the upper Mississippi River Basin states, there were very few comparisons of nutrient removal efficiency compared across a variety of conservation drainage practices. For the agricultural non-point source side of these nutrient strategies, initial strategy development in some of the states started with development of an in-depth science assessment by a team of scientists, aka the science teams. These science teams considered the best available research, along with sometimes expert opinion, to develop practice effectiveness values for a variety of conservation practices. A benefit here was that these effectiveness values were all developed consistently, following the same process, by the same team of experts in each state. I'll show you primarily examples from Illinois, and this is a summary table for the nitrogen loss reduction practices in the Illinois strategy. You see topics that have been covered in this course before, like reducing in-loss by reducing the nitrogen application rate to the MRTN, using nitrification inhibitors, modifying our timing of nitrogen application. Those are all in-field management practices, and you see a range of about 7.5% up to about 20% nitrogen loss reduction. The practice of cover cropping, which is a cereal rye, specifically in this case, comes in a little higher at 30%. And then you see the edge of field practices ranging up to about 90%, and of course the land use change practices, which are consistently very effective for reducing the amount of nitrogen we send downstream. Here's a similar table for phosphorus from the Illinois nutrient strategy. We see about 0 to 50% for the infield and edge of field practices, and again, those land use change practices are really consistently effective for reducing phosphorus loss. In addition to presenting effectiveness values in tables, it's actually much more transparent, I think, to look at conservation practice efficiencies as a graph, like shown here. The important thing this graph conveys that those fact sheet summary tables didn't is the range, or essentially the uncertainty, associated with each practice. Those error bars could reflect a couple of different things. Firstly, a bigger error bar could mean a given practice performs differently in different locations or in different years. That is, we have good data on a practice, that's a scientific known, but the numbers are variable. For example, there are years where cover crops don't germinate at all, and there's years where they do great. A second different reason for a big error bar is due to uncertainty in the data. Perhaps there haven't been very many studies on that given practice, so there's just practice performance information that we simply don't know yet. That's a scientific unknown. Here's another interesting way to reflect uncertainty about practice effectiveness. You see this table from the Iowa Learning Farms group has columns of confidence for each of the metrics you might be comparing practices on. And the check marks range from anecdotal evidence to scientific consensus. That's a pretty big range. My point is, it's useful for scientists to be able to cut to the chase and provide concise and defensible numbers, one number for a given practice for watershed planning purposes, budgeting purposes, and even sometimes for policy purposes. And it's also important for us as scientists to keep those error bars in the back of our minds so we don't present a false sense of precision. As I mentioned, information comparing the effectiveness of multiple conservation practices was pretty thin, especially for the tile drain landscapes, until the process of the state nutrient strategies was initiated. And just like each practice has an error bar associated with it in terms of effectiveness, when the science teams in different states assigned practice effectiveness values, they sometimes came up with different numbers. Here I'm showing the practice effectivenesses reported for Iowa, Minnesota, and Illinois in each of our state strategies for both nitrogen and phosphorus practices. You see wetlands, for example, were rated extremely consistently by the science teams in all three states at about 50% nitrogen loss reduction and no P loss reduction. On the other hand, there were notable differences in the practice effectiveness values for cover crops, for example, with only 10% in loss reduction in Minnesota when the cover crop was planted after corn or soybeans, Bioreactors are another example of differences between states, where Minnesota rated bioreactors at only 13%. Some of these differences are simply based on regional and climatic differences. It is harder to get good cover crop establishment the farther north you go. That's a biophysical limitation of cover crops, not insurmountable, but it exists as a challenge. There may also be differences in the calculation method or how a practice was defined in different states. So if you do want to compare numbers, for example, in a literature review, it's good to take the time to dig in to know exactly what you're comparing. One more nuance about practice effectiveness is that you might be wondering, what if I want to do two practices together, like an infield cover crop paired with an edge of field wetland? Are these percentages additive? Are they multiplicative? In essence, this is the concept of stackability. I want to give a shout out to this great article called Eating the Metaphorical Elephant, where the authors attempted to tackle this issue of stackability. This is a pretty heady example, but stick with me. The top example, top row, shows how practice efficiencies would be calculated when an infield and edge of field practices are applied on separate acres, or in other words, those practices are not stacked together on the same acre. Moving from the left, you have half of your row crop acres get a cover crop, which provides 30% in-loss reduction on 50% of your total acres. And then you also have a wetlands treating the other 50% of your row crop acres. Again, these are different acres because these practices are not stacked in this scenario. Those wetlands give you 50% in-loss reduction on the second half of your acres. Altogether, you end up with an overall reduction of 40% from the baseline, or in other words, 0.5 times 0.3 plus 0.5 times 0.5. In this top example, every single acre was treated by a practice, but there was no stacking. The bottom example shows when those two types of practices are applied to the same acres. In this case, in this bottom example, half of the acres overall didn't get any practice at all. The treated acres get a cover crop, which reduces the in-load going into the wetland by 30%. That means I have 70% of my baseline load remaining, and that 70% gets multiplied by the wetland effectiveness of 50%. 0.7 times 0.5 means the wetland has removed 35% of the initial original baseline load. So the original 30% removed by the cover crop plus the 35% removed by the wetland gives me an overall 65% reduction on the acres that were treated. Coming to the end, remember I was only treating half of the acres in this scenario, so I've actually only removed 0.5 times 0.65, or 33.5% overall. That's a pretty heady example. Let's look at it a different way. In this example, we know our baseline load is 150 pounds of nitrogen, leaving a given field. And we want to do a cover crop paired with a bioreactor. So my edge of field load is 150 pounds minus the product of 150 pounds times 0.30, 30% for the cover crop. That equals 105 pounds of nitrogen remaining in my water after I've successfully done my cover crop. And that's what goes into my bioreactor, the 105 pounds. The bioreactor treats this 105 pounds, and I follow the same procedure. 105 pounds minus the product of 105 times 0.25, 25% effectiveness, and that equals 79 pounds of nitrogen left to go downstream after I've stacked my cover crop and my bioreactor. Overall, we removed 71 pounds of nitrogen from the baseline load, which was a 47% in-loss reduction. You see from this example, effectiveness percentages for stacked practices are not exactly additive. If they were exactly additive, you would have been 30% for the cover crop plus 25% for the bioreactor. But here's the real problem. From a research perspective, we have very little empirical evidence or data from actual field studies documenting how practices impact each other and how pairing practices together impacts their effectivenesses. And so I can show you how to do the math on the screen, and these examples are mathematically correct. We just have very little empirical evidence or monitoring evidence from the field to know how these percentages actually do relate in practice. This is especially glaring for when we pair in-field practices together. Their efficiencies aren't exactly additive, but you have more nitrogen loss reduction than just doing one of the practices alone, obviously, when you stack two practices. We just haven't yet had good controlled studies designed to parse out those specific impacts, especially for all the possible combinations of stacked practices. While we may not have all the answers to quantify practice stackability, we can discuss and compare practices on their relative ability to be stacked. A while ago, we looked at the recommended practices in the Illinois Nutrient Strategy and developed a qualitative ranking for how stackable each practice was. In these rankings that we developed, a high stackability score, which is from 1 to 5, with 5 the highest score, means a practice can readily be used with many other practices. For example, shifting nitrogen fertilizer applications from the fall to the spring can be done on any acre where corn is grown, which means that the practice can readily be used with many other practices. The same goes for many other infield practices like cover crops, which also had a relatively high stackability score in our rankings. In fact, infield practices and edge of field practices often go hand in hand. That is why practices like bioreactors and wetlands also rank highly here. However, it's relatively unlikely a landowner would route drainage from a given acre to both a bioreactor and a wetland, for example. That's not impossible, just relatively improbable to pair those two specific practices for one drain field. So you see not all practices stack equally well with all other practices in all cases. Notice practices like converting cropland into pasture or doing land retirement don't pair with other recommended practices because they're wholesale land use changes. You wouldn't do one of our nitrogen fertilizer management practices on land that had been retired to native grass. However, in these cases, stackability is a moot point anyway, because these land use change practices tend to be some of our most effective practices for improving water quality, so you don't need to stack anything on it. Just a minute ago, I said infield and edge of field practices often go hand in hand. And I want to highlight here a recent report that in a way emphasizes the important stackability of edge of field practices. The Nature Conservancy and other partners released this edge of field roadmap in 2021. And just to quote the report, you see, tackling nutrient loss challenges within the field is not enough. And then later, implementation of conservation practices at the edges of farm fields represents a crucial but underutilized conservation opportunity. Just to sum up, stacking practices will be increasingly important, and we really do need every practice in our conservation toolbox. See you next time.